And good luck studying.
Can I just copy this?
Regions. Hopefully this was helpful.
No.
And
People already have you.
goodbye.
Yeah, I tried to post it on her thing. Okay. Where is it? Oh, it's in Google Chrome. Good. All right. All right, so welcome to the live streaming Regents Review. This topic we are going to be talking about phases of matter. We're going to be talking about phase changes. We are going to be talking about ideal gases as well as the combined gas laws. And we also had some questions about vapor pressure, which I plan to address today. I set up for you a remind for you to send in different questions, and I'm looking for that code right now. The code, if you want to text in, is you're going to text the number 81010 at LiveChem. If you have any questions, feel free. My cell phone is here. I will answer them as I go. So the other thing I want to point out to you is that if you go to the document with the Google, the YouTube video, there's going to be a link on the video, and it says practice questions. There is a document there, and that document is going to have some practice questions for you to work on with me. So I'm going to give you a minute. Please look at that and print the practice questions, as well as register for the remind. Apparently the text is backwards. Give me 30 seconds to fix that on the camera. Hold on. Better?
It should be.
Okay. Just give me 1 second. I think I got a text message in. I just want to check and make sure that we're in business. Recent. Nope. Okay. We good? Yes. All right. So let's talk phases of matter. Okay, sometimes phases of matter can be referred to as states of matter. And if the Regents exam asks you on Tuesday, and how many states does matter exist, do not fall for it. The answer is not all 50 as in like the continental United States of America. There's Long Island, here we are. Okay, not the answer, like not with Alaska and Hawaii, with Guam and Puerto Rico. No, do not fall for it like I did when I was like 17. That's not the answer that they're looking for. When they talk about phases of matter, they are talking about your classic three phases, your solids, your liquids, and your gases. One of the things they like to ask you to do the day of the Regents exam is draw particle diagrams. Solids exist with a rigid, geometric, fixed, repeating pattern. Okay, so if they ask you to draw a solid, okay, you want to make it look like it is a fixed, rigid, geometric pattern. They have a fixed volume as well as a fixed shape. As opposed to a liquid, who is going to take the shape of the container they are in. They are going to have a fixed volume, but they are going to uniformly fill the bottom of the container in which they are in. And notice it is not a rigid fixed geometric pattern. One of the things that often happens in my classroom is that kids will draw a liquid, and some of the time I have to ask them, is that a solid or is that a liquid, because of the fixed rigid geometric pattern. You want to make it very clear that your liquid is not in a fixed rigid geometric pattern by drawing them in not a geometric fixed pattern. The gas particle diagram, a gas is going to uniformly fill the container that it is in. It is going to have no definite shape as well as no definite volume. So put top on it so it can uniformly fill the container and it can take the shape of the container that it is in. Okay, a couple years ago, one of the Regents questions asked what a particle diagram for a gas looked like, and this was one of the answer choices. No, because it's not uniformly filling the container. If this was air, okay, gas particles with like oxygen and carbon dioxide, you would not be living because all of the air would be on the top of the container and there would be nothing for you to breathe. So these are the three classic phases of matter. We are going to dive into gas laws later on and kind of take a talk about gas laws. We're going to hit that towards the end of the topic later on. Okay. There is one other phase of matter that sometimes shows up when they are doing different reactions, and that phase of matter is referred to as aqueous. Okay, and you'll see it abbreviated in a chemical reaction in the subscript, next to the subscript, you'll see parentheses, and they might throw this little phase of matter in there as well. Now, aqueous is a completely different beast than the other phases of matter, and we're going to come back to that picture I drew in a minute. With aqueous, aqueous means for it to be physically mixed with water. And not only does it have to physically mix with water, it has to become fully dissolved into the water. So if you were to take something like NaCl, which is found in its solid form, sodium chloride, and put it into a container of water, you would then have the NaCl split into its different ions and dissolve fully into the water. Now, what you're not seeing in this picture, and just bear with me a minute while I get my magical case of all these fantastic colored pens, is that there would also be little water molecules in here who are hanging out with the NaCl, and you have formed a uniform distribution in a fully dissolved NaCl sample that is now aqueous. Okay, one of the things that they like to point out the day of the Regents exam, I'm gonna just find, no, not gonna work. I'm gonna find a way to just quickly re-sketch this for you, is they like to ask you which one of these is a mixture, and they'll show you a solid particle diagram. They might show you, not even a particle diagram, but just an equation. And they'll show you like a liquid who's not uniformly, just fill in the bottom of the container, but not in a rigid geometric pattern, and then you'll have a gas. Okay, and they'll say to you which one of these is a pure substance, which one of these is a mixture. Okay, just take a quick peek. Notice here that in a solid, in a liquid, and in a gas, there's only one type of atom or one type of molecule in here, which makes these three things pure versus this aqueous thing a mixture, because you have two or more different things in here that have been physically mixed together. These are your three classic phases. They are pure, and they'll throw in aqueous here as a phase, but it is a different type of phase. It's a mixture in which you have, two or more different substances that have been fully dissolved into each other. Okay, just gonna take a quick 2-second look at the remind and see if there's anything that you all sent in. I don't see anything. Okay, really quick, in case you were interested, I'm just going to put this back up. If you are interested and you would like to text in your questions, the number is 81010, and you're going to text that number, put in the message live chem, and I will gladly answer any questions you have as we're going through the different topics. Okay, so one of the things that comes with phases and phase changes is the heating cooling curve, which is the bane of existence for many different chemistry students. But in all honesty, it's actually something very simple. If you are going to take a look at a heating cooling curve, on your x-axis, you are going to find time. Okay, and you are going to be graphing that as a function of average kinetic energy, which is also known as temperature. And if you don't know that temperature at this point is another fancy word for average kinetic energy, well, you need to know that. That is one of those things that shows up pretty regularly. Average kinetic energy is the measurement of movement in a substance, and it is going to be the temperature that you are going to be seeing in that substance. In a heating cooling curve, it has a very classic shape. This, as drawn right now, would be a heating curve, but I'm going to tell you that you can read them forwards and backwards, which means that this is also could be read backwards as a cooling curve. For the sake of making this absolutely stunning, we're going to do a little bit of color coding. If you are reading this diagram going up, we're going to shade this diagram in red to show that we are reading this going up. This would be our heating curve. Now, because this is a physical change, you can, read this forwards and backwards. We're going to shade going down in blue, showing that everything on this backwards end is going to be our cooling curve. So, in a heating cooling curve, we are studying the 3 different classic phases of matter. We are studying a solid, and at time and temperature 0, we would have a solid. And if we were to draw this, we would see a fixed, rigid geometric pattern in our particle diagram. We have this solid, and there is a point at which a solid is going to have enough average kinetic energy or enough movement to decide, I don't really want to be a solid anymore. I want to become a liquid. This point where a solid has enough energy to transition into a liquid is known as the melting point. Abbreviating, I'll write it in for you, melting point. Okay, so this flat line right here, this is the phase change that happens when a solid decides I want to become a liquid, and I'm going to write this in, we call this the phase change of melting. And on this flat line, we're going to have half solid, half liquid, where we are going to be transitioning from the solid phase into the liquid phase. One quick check. Okay. All right. Sorry, I thought we got a message coming in, but we don't. All right. So after this solid has turned into a liquid, we now have on this slanted line all liquid. And if we were to draw this in a particle diagram, we would have taking the shape of the bottom of the container, but not uniformly filling it, definite volume. This slanted line right here, this liquid is going to become warmer and warmer and warmer and warmer over time because it's a heating curve. And there will be a point where a liquid says, I am too hot to be a liquid anymore. I now want to become a gas. And this point is called the boiling point. I'll write that out for you. The boiling point. And this is the point where a liquid is going to start transitioning into a gas. Okay, this phase change is called boiling. Okay, sometimes you can see the word vaporize. Another fancy chemistry word for this is to evaporate. These are the phase changes that exist on your liquid gas line. Now, after this gas has fully transitioned from the liquid into a gas, we now have pure gas. That sounds really wrong. We have pure gas that is going to, continue to heat until it is in its gaseous form forever and ever, and it will continue getting hotter and hotter and hotter. So this is a heating curve. Everything going up this diagram in red is a heating curve. I actually meant to color code these bad boys in red for you. So let's do that. These are our red phase changes, just for the sake of making this consistent. Okay, we're going to call this melting, and this is a red word because it is going up the heating cooling curve. Let's make this nice and clear so you can understand what's going on here. This is our heating curve. Now, hold on, just checking the remind. Okay. Nope. Again, I thought you were sending me messages. Maybe you are sending me messages. What the heck's going on? 9 new messages. I don't see anything. Okay, if you are sending messages and you're not getting through, there is a group chat function on the side that you can send messages that I can also look at too, because I'm hearing my phone beeping, but I am not seeing anything in my remind. Don't know what's going on with that. All right, so let's go backwards here. This is our heating curve. Well, if you can physically heat something, you can physically cool it down. And you're just going to read this backwards. This is a gas, and we should actually just draw in our particle diagram. A gas is going to uniformly fill the container. It is going to, take the shape of its container, has no definite volume, and it is going to start to cool on this cooling curve. So a gas starts off super hot, and it's going to get cooler and cooler and cooler and cooler and cooler. And there is a point at which a gas says, I am too cool to be a gas anymore. I don't want to be a gas. I'm too cool. I am going to transition back to the liquid phase. This point right here, where a gas says, I am too cool to be a gas anymore, is called the condensation point. And we are going to label that condensation point. Just checking our mind again because I hear beeping. Nothing is showing up. All classes. Oh, I found you all. Okay. Hold on. We're going to hit the pause button. I have some messages that just came in. Oh, no, that's about the actual live streaming. Okay, someone just told me it's backwards. Okay, those are also classic shapes. No? Hold on. Oh, it's backwards. Yeah, we're good. We're good. We're good. Okay. Okay. All right. We fixed the backwards. Thank you, Annalisa. Thank you. I'm really sorry. This is my first time doing a live chat. Hopefully, it's gonna get better. Okay, Megan, what is kinetic energy? Don't you worry, Megan. Hanakato, I hope I said that right. I will absolutely get there. When is it increasing? When's it decreasing? I have to clearly make my color-coded diagram before I can explain that to you so you can truly understand what's going on. Hold that thought. I'm coming back to you. Next question says, when the diagram hits a flat plateau, don't you worry, you are on the same page as Megan. Danny McDonald, I'm coming back to you as well. Bridget Kennedy, can you go over, sublimation and deposition? Sure, hold on, I'm getting there. We're not ready. It's going to be on the diagram in a minute. I cannot pronounce this. Okay. I can't say your name. With an increase in average kinetic energy, is the entropy increase? Hold that thought. Hold that thought for a second. We're going to get to entropy in a minute. So now that I figured out what's going on with this remind and the live stream and the chat, I'm just going to leave this here. More comments below. Okay, great. So let's keep going here. You have your condensation point, and this is your gas is going to cool, 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 cool. Oh, look, here's the point where a gas says, I'm not going to be a gas anymore. I'm too cool. I am going to start to condense into a liquid. So this is the phase change called condensation. I'm going to color code this bad boy in blue so we can see that these words are going with our cooling curve. And don't worry, because this is going to be related in a minute. So now I have my liquid. My liquid is going to start to cool, 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 cool. There is a point where a liquid says, I am too cool to be a liquid. That point is called the freezing point. And we're going to write that out for you. It's an F, by the way. Freezing point. And this phase change of freezing is called freezing, but there are other words they like to use called crystallization, which is the process of forming crystals, hence why it's in its crystal form, not in its liquid form, as well as solidification. These are all synonyms for the same process. So we have ourselves our beautiful, beautiful color-coded diagram. Stunning. Okay, so of course, I had to bring a couple props for you. This is a little guy. He's like a man, policeman, and he is going to go up the heating cooling curve. Now, in class, when I explained this, I explained that this is like a staircase, and if you are going up the staircase, you are entering the staircase. So he's like, oh, look, I'm a solid. I'm entering the staircase. Enter, 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 enter. When you go up the staircase and you're entering, oh, look, I broke his legs. You're entering the staircase. These entering or heating things, enter is like endothermic, because you are entering the energy. Oh, look, we're kind of off the screen. Okay, endothermic, entering the energy. Another way of saying entering is to absorb. energy. As you go up the heating cooling curve, here's the man, enter, enter, enter. Oh, look, you're gonna go from a solid into a liquid. Oh, you have to absorb energy because that's endothermic because he's entering the staircase. Okay, now it's really cool if you think of this like a staircase, because when the guy's like, hey guys, I just finished work, it's time to go home, and he's going to go home, he's gonna exit the staircase. He's like, oh look, I gotta go home, my car's on the other side. Exit, 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 exit. As he exits the staircase, and you go from top to bottom, and you exit the staircase, well, it's really cool. Exit is like exothermic, which means you have to exit or release the energy in order for you to perform those physical changes. So as you go up the heating cooling curve, when you go from low to high, you have to absorb energy in order to do so. Now, by the way, that's like an underlying theme of this chemistry curriculum, that when you go from low to high, you absorb energy. Does that kind of maybe sound like this thing called spectra? Oh, if you need to know the story of spectra, go back and maybe listen to the atomic theory story when you watch the live stream, because this is an underlying theme of chemistry. When you go from low to high, you absorb energy. Oh, when you go from high back to low, you have to release energy. And in spectra, because that's, again, underlying theme of this curriculum, you release energy in the form of light. Well, in the heating cooling curve, when you go from high back to low, or you are releasing or exothermically doing things, you are releasing energy back into the environment. So, just taking a quick check at the live feed. I'm sorry, can you go over sublimation? Yes, hold that thought. Moth crystals, naphthalene. Okay, hold that thought on the moth crystals and the naphthalene. There are two sublimation things that we do need to address. And, you know, there's two that the Regents exam loves to ask about. Hold that thought on deposition for 1 second, Caitlin. I cannot pronounce your name. And Danny McDonald says, I also want to know what phase change is fusion associated with? Are you talking about nuclear fusion? Danny McDonald texts back in, when I think of fusion, I am thinking of a nuclear reaction. And I would say to you that when you're using fusion, if anything, I'm going to put fusion down here, but I never use that word in my classroom. So Danny McDonald, when you get a second, text me back in. I don't know if you're talking about nuclear or if you're talking about phase change. And I will gladly figure that out for you. So these are your classic phase changes in your heating cooling diagram that the Regents exam clearly loves to ask about, but there are two other phase changes that have come up kind of, I guess, regularly on your text-ins, and it is the phase change of sublimation. Now, the really cool thing about sublimation is when a solid just has enough average kinetic energy to magically transition its way into a gas. And it happens sometimes. If you ever, you know, seen like on Halloween, you've ever seen on Halloween, like the really spooky Halloween cauldrons where like smoke's coming out at a party, that is something called dry ice. I'm gonna have to just come back to this in a minute. Don't worry, I'm gonna come back. I know it's beautiful. When you talk about sublimation, it's what you see in dry ice. And with sublimation, what happens is you are taking a solid and it is skipping the liquid phase and going directly into a, I'm sorry, hold. It is skipping the liquid phase completely and going directly from a solid into a gas. Now, if you think about little man and he's like, oh, look, hey, I want to go from a solid to a gas, he has to enter the staircase. When you go from solid to a gas, it is endothermic because you have to absorb energy in order to get up that staircase. Now, this phase change of going from a solid directly to a gas is just known as sublimation. It's just the name of a phase change, just like melting a solid to a liquid, just like boiling is liquid to a gas. Well, sublimation is just going from a solid directly to a gas. There are two sublimations that happen that the Regents exam loves to ask you about it. And that is carbon dioxide, which is what you find in spooky Halloween cauldrons. It's dry ice, and it turns directly into a gas. This is like the big one. I would say to you like 90% probability they're going to ask you about carbon dioxide turning into solid, turning into carbon dioxide gas if they ask you to identify a sublimation. Now I'm going to say like the remaining like 9%, notice it's only 99% at this point, would be iodine solid turning into iodine gas. These are the two the Regents exam loves. They love them. At the same time, it doesn't have to be these two. The definition of sublimation is anything from a solid to a gas. So they could be like, your mom solid is turning into your mom gas, and guess what? It would still be sublimation as long as it's solid into a gas. Your mom is not an element or a compound or a mixture, so please don't tell her I said that. All right, at the same time, because this is a physical change in which you are going from a solid to a gas, anything physical you can reverse because you're physically doing it, which means if you can go from a solid to a gas, guess what? Little man can exit the staircase and be like, hey, I'm gonna go from a gas to a solid, and it can happen. When you go from a gas into a solid, it's just called deposition. And off the top of my head, I don't remember a particular deposition reaction where you, or phase change where you're going from solid to a gas, because this one's really not asked a lot about the Regents. And I don't remember one off the top of my head, but I do know that the Regents exam loves these two with sublimation when you're going from a solid directly to a gas. These are the two the Regents exam loves to ask about. And I see some of you were like texting on the chat, your mom. Yeah, I was just making a point that it doesn't have to be these two. It could be anything as long as it's going from a solid to a gas. That's why your mom's there. Okay. So I'm just going to take a quick look at what's the name of the phase change if it goes with okay, Danny McDonald, you asked if fusion, I'm coming back to you, you wanted to know what fusion. I'm going to say fusion is going into a solid, so a liquid into a solid, but hold that thought for a minute because I will look into that a little bit more deeply for you. Oh my God, fusion, what am I talking about? The heat of fusion. Danny McDonald, I'm really sorry. This is my first time doing a live feed. Hold that thought for a minute because I promise you I'm going to get there. It took me off. I'm sorry. Okay, Danny McDonald, this one's for you. So for the sake of not using the same really scary looking diagram that I made that's like crazy messy, let's just neatly tidy this up for a second. You have solid, you have liquid, you have gas. This is your phase change of going from a solid to a liquid. This is your phase change of going from a liquid to a gas. Okay, if you are going up the heating cooling curve, this phase change is called melting. Okay, if you are going up your heating cooling curve, going from a liquid to a gas is called boiling, vaporizing, evaporating, and awesome. As you are going down your heating cooling curve, this phase change of going from a gas back to a liquid is called condensing, condensation. And if you are going down and you have a liquid turning back into a solid, you have this phase change, which would be called freezing, solidify, crystallize. Danny McDonald, I'm really sorry because you caught me off guard for a second. I obviously know what you're talking about because the heat of fusion is one of those reactions you really do need to know. Now, when I do this in my classroom, and those of you that asked about where kinetic energy is changing and potential energy is changing, I'm going to tie that in right now. So just don't worry, it's coming. When I do this in my classroom, I have my kids cut this diagram on its point. So like this here was the, clearly we need a different color, hold that thought. This was the condensation point, which notice water condenses and water boils if you extrapolate this over at like the same point. Oh, how the hell does that happen? We'll talk about that in a minute. And notice that water freezes and water melts at the same temperature. Again, wait, what? You just put my mind. Yep, it happens. This is at the same temperature for a really good reason. If we cut this diagram on its points, okay, there are 1, 2, 3, 4, 5 distinct different points on this 5 distinct regions on this diagram. Now, if you go to your best friend in chemistry, also known as your chemistry reference tables, and you go to the back page, there is this thing called the heat formulas that you would be using in order to do these problems. Notice there are 1, 2, 3 heat formulas, and there are 1, 2, 3, 4, 5 different regions of the heating cooling curve. Now, I don't really know math that well, but I'm pretty sure if there's 3 equations and there's 5 different regions, that you're gonna have to use some of the equations twice. And that's actually very true. There are 3 regions that you are going to share the same equation because there's 3 regions that kind of look the same. And if you look at this diagram, you notice that in region number 1, the line is slanted. Now, if you to go back to what these axes are, this was your time, and this side was temperature, also known as average kinetic energy. On this line right here, oh look, the temperature is changing because on your slanted lines, temperature is changing. Oh, let's write that down. Here we have a change in average kinetic energy because, well, the line's slant, like the graph tells you that, it's slanted. Now, notice this flat line, this plateau. If you extrapolate this over, it's like flat, flat, flat. Oh, look, it's not changing because on your plateau, the average the average kinetic energy is not changing. Okay, on this slanted line, oh look, it's changing because the temperature is changing. On this line, the average kinetic energy is changing. Oh, flat line, not changing the average kinetic energy. And on this line, okay, average kinetic energy is changing. So somebody asks, oh, where do I know if the average kinetic energy is changing? Well, it's on the graph. If you look at the line and it's slanted, well, it's changing because it has a slope. If there's no change, well, it's a flat line, your average kinetic energy is not changing. Now, the way this works is that if your average kinetic energy is changing, well, the potential energy is staying the same. So here, potential energy is the same. On this flat line, well, the average kinetic energy is not changing, which means something has to be happening. When little man, here he is going up the heating cooling curve, he's absorbing. Oh, look, oh my God, well, he's still going up the heating cooling curve. It's just that the energy is coming in a different form. It is being absorbed in the form of potential energy. So our potential energy is changing on this flat line so it can undergo the physical phase change. Now, I think of potential energy with a P. I think of plateau with a P. I think, oh, potential energy, plateau. Well, my potential energy is changing on this phase change because all these things are P's. So now if you keep going here, the average kinetic energy is changing on the slant. Well, the potential energy is staying the same. And here, the average kinetic energy is not changing, so my potential energy is, and if this average kinetic energy is changing, well then my potential energy is staying the same. So that is the deal with potential energies and average kinetic. Danny McDonald, I promise I'm coming back to you right now. You asked about the different that word fusion. Well, let's go back to this. When I take a look at my 1, 2, 3, 4, 5 regions, but only 3 equations, clearly there has to be some sort of overlap. When I have my kids in the classroom assign their different equations, what I like to look at is I say, okay, well, there's 3 equations. Let's start with the one that I clearly see the word on the heating cooling curve. You have Q equals mHV, and that is your heat of vaporization. If you take a look at this heating cooling curve, well, the word vaporization is in region number 4 because that is the physical phase change. When you use, clearly, here's some different colors. When you use the first equation, for region number 4, we are going to use Q equals mHV because the heat of vaporization is what we need in this region, okay? And because it says the word vaporize, this basically is your trigger word for region number 4. When you see the equation Q equals mHV, we know to use this formula in region number 4 because the word vaporize fits in this equation. Now, here's the deal. Any of these words are synonyms for use Q equals mHV. So you see the word boil, HV. HV. Vaporize, oh, evaporate, they're all HV. If it says to you a liquid is turning into a gas, well, last time I checked, that's just the fancy way of saying that this is vaporizing. You're still using HV. Now, this is the tricky part. Yes, it's condensation, but it still fits into region number 4 because you are still performing this phase change. You're just doing it backwards. So if you see the word condensation, you're using Q equals mHV. Now, if you go back into the reference table and you take a peek, they're telling you that Q is heat, they're telling you that that M is mass, and they're telling you that HV is the heat of vaporization. Now, if If you don't know any better and you're like, well, how do I know in a problem which one is which? Because I don't know, they're giving me all these crazy numbers. If you go say, okay, well, I want to work with my heat, and we look up heat, well, heat is always in joules. So I know in a problem that if I see joules in here, I'm working with Q. So Q is always in joules. It is the measurement of energy, also known as heat. Okay, M is grams, because it's our math. It says graph. Why did I write that? Okay, grams. And then your HV. Your HV is a constant. And the way HV works is it is a set amount of energy in joules per gram of a substance that is required in order for you to transition a liquid into a gas. If you are going up your heating cooling curve and you are absorbing energy, well, you are going to have to absorb this set amount of joules per gram in order to transition this. If you are going to be cooling, you are going to have to release or subtract or remove that set same amount of energy, joules per gram, in order to make that transition happen. This is the reason why water boils and water condenses at the same temperature. If you're at the temperature and you absorb that amount of energy, well, you're going to become a gas. If you are a gas at that temperature and you subtract that amount of energy, you're going to become a liquid. This is the reason why this point is the same, and it has to do with your heat of vaporization. Now, if your substance is water, they are going to give you the heat of vaporization on your reference table. On reference table B, the heat of vaporization of water is 2,260 joules per gram. Joules per gram. If your substance is water. If your substance is not water, you cannot use that piece of information because the substance isn't water. They are going to have to tell you that piece of information, or they are going to have to give you Q and they'll give you M, and then they'll make you solve for that in order for you to figure out, you know, what the heat of vaporization is. Now, this is your trigger words for doing Q equals MHV. The next region I like to focus on in the heating cooling curve is region number 2. So Danny McDonald, one more time, we're coming back to you. This particular equation, if you take a look, back to the reference, oh, look, this fell off. Okay, this equation, the next one, Q equals MHF, this one's a little bit trickier. This is your heat of fusion. Now, I really like Q equals MHV because in HV, like the word vaporize is like right there, and like it's so easy to pick out. When I do heat of fusion with an F, okay, I'm like, oh, well, where am I going to find that on my heating cooling curve? F for fusion, I think of freeze with an F. So these are the trigger words that mean heat of fusion. And I need to do that particular math when I get there. So heat of fusion, if I see the words melting, well, that's a trigger word for the heat of fusion. Even though it's not freezing, it is still the same physical change, just going backwards. Okay, if I see the word freeze, dead giveaway for fusion. Solidify, fusion, okay, crystal fusion. These are all key words for pick this equation. If it says solid to liquid, liquid to solid, these are all your synonyms for picking Q equals MHF. Again, Q is in energy, and it is in joules. M is in grams. Why am I writing grams? Okay, in grams, because it is the mass. Oh, I figured it out. Mass and grams combined is grams. Okay, and then the last one here is HF, which is your heat of fusion, which again, can you see any of that? Okay. Okay, heat of fusion, which again is a constant. It is a set amount of energy that is required in joules per grams for you to make the transition from a solid into a liquid. Now, if you are going up the heating cooling curve and you are already a solid and you absorb the energy, you are going to transition into a liquid. If you're a liquid and you start to cool, you are going to transition back down because you will exit that energy. Again, notice the temperature at which water melts and water freezes is the same. It's just that you are absorbing that energy to go up, whereas you are releasing that energy to go down. Now, we have used 2 out of the 3 equations. At this point, we now need to use the final equation. So we use 2. There are 3 remaining equations left. I'm sorry, 3 regions left. Notice what is the same on region 1 and region 3 and region 5. Temperature change, temperature change, temperature change. Oh, look at the last equation that they give you from on your reference table. There's Q, there's M, there's C, delta T, which stands for change in temperature. I get kids all the time who try to use MCAT in this region, but last time I checked, like, the temperature is the same. How can you do an equation with math when they want the variable to be temperature change when there's no temperature change? So we are going to use Q equals MCAT for regions 1, 3, and 5. So let's put those guys in. 1, 3, 5. These three equations are going to share Q equals MCAT or MC delta T, depending on who you speak to. It's like tomato, tomato. Q is still in joules. M is still in grams. C. Hold that thought on C for a second. Let's do delta T first. Delta T is the change in temperature. Now, when you do change in temperature, you want to do final minus initial because that is how delta is done, okay? If you do this in a different order, some kids are like, I will always subtract big from small. No. You will always subtract small from big. No. You will always subtract whichever one is final versus whichever one is initial because it will make a difference in the sign of your temperature change, which actually tells you something really important. If your sign of your mathematical answer is negative, that means that you subtracted the energy out, and it's kind of like your self-check. If your answer is positive and you end up with a positive answer, it means you absorbed energy. Now, the day of the regents, they don't care if it's positive or negative. They're just asking you for a numerical value. But if you get a negative number off your calculator, don't have a nervous breakdown. Don't cry. Like, don't be like, I quit the regents. Just wait a second and look at your phase change. If they're telling you you're going from a gas to a liquid and you got a negative number, well, that's okay. That's actually really right because you have taken that energy out because you've gone down the heating cooling curve. So when you do your temperature change, you are always doing final minus initial, and that actually will make a difference later on if they give you one of the harder problems where they're asking you to solve for a different temperature. Like, they're giving you everything and they want you to solve for the final minus the initial, like, you know, which one's final or which one's initial. Now, again, okay, Q is joules, M is in grams, C. C is another one of these constants, which actually we forgot to do the constant for HF. 2 seconds. HF is another constant. If this substance is water, it's on the front page of your reference table, and it is 332, 334 okay, joules per gram. If your substance is not water, they're going to make you solve for it, or they're going to give it to you. Now, C is another one of these situations where it is a constant. Hopefully you can read what I'm writing. Okay, C is another one of these situations where this is a constant, and this is the amount of energy it takes to raise the temperature of a substance 1 degree Kelvin or Celsius per gram, per gram joule. Oh, I gotta look at the unit on that, but this is the idea. It's another one of these constants where it is the amount of energy it takes for you to raise the temperature 1 gram of that substance 1 degree Celsius. What's the amount of energy? This is not right. Okay, so basically this is a fact. This is another constant, and if your substance is water, this is going to be 4.18 joules per gram degree Celsius. I knew the units were wrong on that. Okay, joules per gram degree Celsius. And if it's not water, they have to give it to you, or they are going to make you solve for it. So I'm going to just take a quick pause because that was just like 1,000 things that I put on the paper. I want to just check their mind. I'm going to give you a minute before I transition because there are still 17 more minutes left, and I want to touch base with you about gases because that was a big idea, and vapor pressure was another question that somebody asked. I got on the pre-asked questions, and Danny McDonald, hopefully I got your heat of fusion question in. Let me know if that if I answered your question. Oh, Caitlin. Look at that. Okay, Caitlin just sent a message in. She said for deposition, you can go from water gas to water solid. Snow, freezers, frost. Caitlin, awesome job. Thank you. The reason why I don't know deposition off the top of my head is because I've never seen a Regents question asked where I can tell you with certainty that if they ask you a sublimation question, it's going to be carbon dioxide solid, carbon dioxide gas, you know, iodine is the other big one. I've really never seen a question with straight up deposition asking you to identify them. But Caitlin, thank you for sharing that. I'm going to give you guys like another like 10 seconds to see if there's anything you want to text in on anything heating, cooling curve related before I move on and I start to touch base with you, because vapor pressure was a big one that I saw, and gases, and I can probably do both of them in the next 16 minutes. Somebody asked about effusion on the you know, pre-selected questions that people had sent in. The deal with effusion is you will never see it the day of the Regents exam. It's not on the curriculum, and I don't want to, you know, spend the 16 minutes going over that. At the same time, you have access to me through Remind. If you just are dying to know a chemistry effusion question, feel free to text in. I'm going to give you 10 seconds to send in any other questions, and I'm just going to check the feed. 10 questions if there's anything you want to ask me. Right? Okay. Okay, Danny McDonald, you're welcome. All right, let's talk about vapor pressure, because that was another big one that came up more than once on the pre-selected questions. Oh, those are my dogs, by the way. Thank you. Okay. Penny Pabin, yes, that is Chester. All right, this is not what I meant. Did you get them out? We're back. Okay. So, sorry about that. I have two dogs. One of them is an absolute dream, and the other one is a real pain. Okay, vapor pressure. The deal with vapor pressure is that it is a measurement of the amount of pressure, also known as force, a gas can exert on its liquid phase in a sealed container. So, on your reference table, there is a reference table called Table H, which is the vapor pressure of 4 different liquids. There is propanol, ethanol, water, and ethanoic acid. So, what I'm going to do is I'm going to actually write that out for you. We have propanol, we have ethanol, we have water, and we have ethanoic acid. Okay, sealed containers. Okay, sealed containers. And we have liquid on the bottom. Liquid, liquid, liquid. Now, if you read reference table H, this curve is showing you the vapor pressure trend, and this oh, that's my hair. This vapor pressure, I'm sorry, this line right here is what we call standard pressure. And when standard pressure intersects with the vapor pressure curve, this is what we would call the normal boiling point. So if I were to read this for you, and you can hopefully trust my graph plotting skills, propanol's normal boiling point is going to be 50 degrees Celsius. Now, at the same time, here's ethanol, and ethanol is going to boil at about 74 degrees Celsius. Our water, hopefully you know this, boils at 100 degrees Celsius. And last but not least, we have ethanoic acid, which boils at like, that's 10, 10, 15. We're going to go with like 118 degrees Celsius. Now, each of these different substances has a unique different boiling point. And what happens here is that the liquid is going to be exerting a physical force because it's a liquid. And at the same time, there is going to be some air that is trapped in the container that is exerting an equal but opposite force, which means that this particular substance is staying in the liquid phase because there's not enough force to overcome this. Now, to overcome and become a gas. Now, what happens here is that we are going to start at time and temperature 0, and at time and temperature 0, none of these have achieved their boiling point. And is this 50? It's 50? It's 55. 55. Sorry about that. I knew that. I wrote 50. Okay, so now what's going to happen here is at time and temperature 0, that these are all still in their liquid phase, we are going to start to heat up the substances. And as they start to heat, there starts to be more average kinetic energy. They start to move faster. And you are going to start to go from 0, you're at 10, you're at 20, you're at 30. You are increasing the temperature. All of a sudden, you hit 55 degrees Celsius. At 55 degrees Celsius, some of these liquid particles have now found the ability to go from a liquid into a gas, but they are trapped inside of the container, which means they are exerting more pressure and more force on their liquid form because they have started to boil. Now, at 55 degrees Celsius, this is the only substance that starts to boil, so it means it has a higher vapor pressure. Higher vapor pressure. And the reason being is because it has been boiling longer. It started to boil first. So we're going to write boiling first. And it is because it has a low boiling point. At 55 degrees Celsius, propanone is the only one boiling. So we're going to hit 60, we're going to hit 65, 70, 75, well, that's actually 74. All of a sudden, well, at 74 degrees, ethanol finds enough energy to overcome this particular situation and start to exert more force because now you have more gases. Well, at 74 degrees Celsius, what is still happening in the propanone container? Well, it's still over 55, which means this thing continues to boil. Even though this is now boiling, this guy is still boiling, which means it still has more vapor pressure because it has been boiling longer. It has a lower boiling point. Let's talk water. At 74 degrees Celsius, water is still a liquid, but at 74, 80, 85, 90, 95, oh, look at 100, water's like, yeah, it's time for me to become a gas, and it starts to boil. But at 100 degrees, ethanol's still boiling. Still boiling, which means even though this just started boiling, it has vapor pressure, or more of it now. This guy still has more because he's been boiling longer, but still has less than this guy because, well, he's been boiling the longest because his boiling point is the lowest. At 100 degrees, ethanoic acid still like, yeah, I'm a liquid, not boiling at all. Once we achieve this point of about 118 degrees Celsius, the ethanol starts to boil. But at 118, water's still boiling, ethanol still boiling, and propanone's just like I've been boiling this whole entire time. So the moral of the story with vapor pressure is that if you have a high vapor pressure, it is because you have been boiling longer. And the only reason why you would be boiling longer is because you have a really, really low boiling point. At the same time, if you have a low vapor pressure, it is because you have been boiling for less time. And then pretty much that means that you have a higher boiling point because it's been boiling for less time because it takes more energy to achieve that. Now, the other thing that shows up pretty regularly is that if you have a boiling point, they like to make the connections to intermolecular forces of physical attraction. It's an F, by the way. So the idea here is that if you have a higher boiling point, you also have a higher intermolecular force of physical attraction because it is harder to separate. If you have a lower boiling point, that means you have a lower intermolecular force of physical attraction, which means it is easier to, separate. If I could summarize for you in one quick summary, if you have a low vapor pressure, why? If you have a higher vapor pressure, it is because you have a low boiling point. And boiling point is directly related to intermolecular forces of physical attraction. And if you have a high vapor pressure, you have a lower boiling point because you've been boiling longer. If you have a low vapor pressure, that means you have been boiling for less time, which means your boiling point is higher. And boiling point is directly related to intermolecular forces of physical attraction. Vapor pressure. 10 seconds, text in any questions you have. And then we're going to transition into gases because I still have 6 minutes. Okay, Alexander Mendel, I just saw something on the live chat stream. It says if they give you C in another unit other than grams, does M remain in grams? Does it have to change for another unit? Alexander, I don't know who your chemistry teacher is, but if they were giving you C in another unit besides grams, that's a really tough, weight. It's hard. So props to you for being able to do that. No one will ever give you C in another unit besides grams. You'll never have to do any conversions. The C will always be in joules, grams, degrees Celsius, and the same thing with HF and HV. They will always be in joules and grams. You will never have to do any sort of conversion with that. Okay, and I hear my phone beeping, and then I'm going to get into gas laws in like literally the next 6 minutes because I probably teach it in like 3 periods. Okay, Caitlin, did you touch on naphthalene, or is it not really? I've never seen any questions on naphthalene explicitly where they're like asking you to know facts about it. If anything, like I've seen, about like deposition, or not deposition, sublimation, but it's more of like in a reading. I've never seen a question where they explicitly ask you about that. All right, gas laws and ideal gases. Here we go. All right, so the idea with ideal gases is a theory that explains the behavior of a gas. If you would like a gas to behave ideally, there are 2 conditions that will make a gas behave ideally: high temperature and low pressure. And the way you want to think of this is that a gas wants to spread out. The higher the temperature, the more it can spread out. The less pressure there is, well, guess what? It's not confined by anything, so there won't be a problem for it. As you do ideal, you kind of want to compare it to real gases simultaneously. Well, if an ideal gas is high temperature, low pressure, well, that means that a real gas is going to be low temperature and high pressure. The way I have my kids remember this is the idea of vacation. Okay, I call the vacation theory the ideal theory because when you're on vacation, you're most ideal. Think about it. You're going to be on a beach in about like 2 weeks, not even like a week, and the temperature is going to be really high and the pressure is going to be really low because like that's ideal. You're on vacation. In real life, that's kind of like, the rest of the school year, like midterm week, and the temperature is like really low and the pressure is really high because you got like tests all the time, your juniors and sophomores, all that great stuff. That's real. So if you want to talk about the properties of an ideal gas, the ideal gas is going to be in constant random straight line motion. And the reason why they are in constant random straight line motion is because they have weak physical forces of attraction. And because they have very small masses. Think about it. Gases need to float, small mass. So the most ideal gas that is out there is something like helium and hydrogen because they are really, really tiny and they have weak forces of physical attraction. He is a noble gas. He's like, I'm too interested, I'm too noble to be interested in playing chemistry with anyone, so I'm like not attractive. And H2 is a non-polar molecule. And he's really tiny, so he's like, yeah, I'm really not that attractive either. At the same time, real gases, well, their motion is more like curved because they have physical forces of attraction. And they are larger, which means that they are not behaving like a gas because they kind of maybe sink to the bottom. Now, there is another acronym that sometimes helps that sometimes other kids use. I like the vacation theory. There is something called PLIGHT out there, and I have not taught this in a really, really long time. Pressure, low. Hold on, somebody help me out here. There's a girl, I can't read this. No, not a girl, Geo. Okay, I've never really, I don't really use PLIGHT, but somebody help me out here. Okay, pressure low, ideal gas, high temperature. It's the same thing. Pressure low, ideal gas, high temperature. It's the same exact thing with the vacation theory. So let's move on here. There is something that they like to ask you about. I literally have 1 minute, so we're gonna make this really snappy. They like to ask you about the different relationships between pressure, temperature, and volume. And there is like this acronym or the story I like to tell about the president, the vice president, and the treasurer. If they like to ask you about the different relationships that exist between the pressure, the volume, and the temperature. Now, the treasurer controls all the money, so if the president would like to get anything done, he needs to have a direct, good relationship between the pressure and the temperature. The same thing exists with the vice president and the treasurer. If the vice president and the treasurer would like to get anything done, he needs to have a direct, good relationship. Now, I've watched one too many episodes of that really terrible TV show 24, where the president and the vice president hate each other. And clearly they liked each other in the beginning, but they don't like each other anymore because they hate each other. And, you know, they're like, this president's going to paranoid. The vice president's like, I'm going to kill him for a job in my sleep. Well, this relationship is inversely related between the president and the vice president. Okay, a lot of kids are like, oh, look, it's like indirect. That means they hated each other equally over the course of the presidency. No, it's gotten like way worse over time. They clearly liked each other in the beginning because they were running mates. Over time, it has gone progressively worse. The relationship between president and vice president is inversely related. Ladies and gentlemen, that is the end of my hour. If you have any questions, you have access to me through the live chat, through the Remind. I think I did everything I needed to do. I did not do any ideal calculations, but there is a practice set of questions on the website for you, like on the link for the YouTube. And if you have any questions, please feel free to send me a message. Good luck. Good luck. Friendly reminder, the test is on Tuesday in the morning. Good luck.